This conference will now be recorded.
We'll jump right in, and yeah, we're recording this, so very good. Okay, so the seminar outline, I'm going to start with Opportunistic Pathogens 101. What's the kind of most basic overview that we need to be aware of so that we can kind of speak intelligently about opportunistic pathogens. So the first question to answer is, why are they called opportunistic? What's opportunistic about them? And the reason that we call them opportunistic is that from a clinical standpoint, they infect mainly people that are immunocompromised. So this could be elderly people, people with a weakened immune system, with underlying respiratory issues, or even certain lifestyle factors like heavy alcohol abuse and smoking. They can infect healthy individuals as well, but healthy individuals are much less likely to get sick after they've been exposed than immunocompromised people. But they're also opportunistic from an environmental standpoint, and we'll talk about this a little bit later, about their relationship with other microbes in the water for how they actually adapt and can survive in the drinking water environment. Okay, so who are they? So we're talking about opportunistic pathogens. Of course, we've probably all heard about Legionella or Legionella pneumonia. It causes about 2 cases per 100,000 or per million people each year. It costs us about $430 million per year, and that's just with respect to the healthcare burden. That's not regarding prevention and treatment in the plumbing side of the system at all. And it was the cause of all 31 reported respiratory waterborne disease outbreaks from 2007 to 2010. So it's kind of the one that's on everybody's radar, and it's kind of the highest priority, if you will, from that sense. But there are other opportunistic pathogens that cause disease to an equal level as Legionella. So these include Mycobacterium avium. It's another bacteria that causes a similar lung infection, and it occurs kind of at epidemic levels with people that are over 60 years old. In terms of healthcare costs, it has pretty much an equal burden to Legionnaires' disease, with $425 million per year. And we've only really recent is in the last 10 or 15 years, linked it to potable or building water system exposures. So that's important to note. It's kind of come up more recently. There's also another bacteria called Pseudomonas aeruginosa. It is the 6th leading cause of HAIs, or hospital-acquired infections. It causes a lot of skin infections, especially with people who have severe wounds and burns that are in intensive care, and it can come from the potable water system as well. There's another bacteria called Acetobacter baumannii, and about 1 in 5 ventilator-related lung disease comes from this bacteria, and it can also grow in potable water systems, very common in hospital systems. But these opportunistic pathogens, while these are just a few examples, they're not all bacteria like these examples are. There's also amoeba, which is a different type of single-celled organism. And the most prevalent example here is an amoeba called Naegleria fowleri, and it was termed the brain-eating amoeba because when you're exposed to it, you have to kind of aspirate water. It gets into your nasal cavity, and the amoeba actually digests and feed on your brain. So it's the brain-eating amoeba. And it has a couple of very high-profile cases linked to drinking water systems. Thankfully, these are exceedingly rare, but they're also nearly 100% fatal, but very, very rare. And when we're talking about this type of waterborne disease, there are several paradigm shifts that we should be aware of in terms of the treatment and approach to how we deal with these opportunistic organisms relative to other organisms. And so the first paradigm shift that I want to tell you about is the etiology of the disease. In other words, what organisms actually cause the disease. So if you look at the number of waterborne disease outbreaks historically, we've seen a decrease in the number of outbreaks, which is a very positive thing. And we've gotten better at identifying what organisms are causing disease. So back in the 70s, when the EPA was really getting started and we started to have more monitoring and regulation of our drinking water, we had a lot of unidentified etiology, so we didn't really know what organisms were causing waterborne disease, and that's diminished in the recent 15 or 20 years. And the primary cause back in the 70s of waterborne disease was traditional pathogens or fecal-related pathogens like Cryptosporidium or Giardia. But in more recent years, 30 to 80% of waterborne disease outbreaks are actually caused by Legionella. And so that's just one of the opportunistic pathogens that's become more prevalent as we've gotten better at treating the water. So we've seen a shift from these bacteria and parasite organisms that are fecal related to environmental microorganisms that are pretty much always present in aquatic environments. So Legionella, as the poster child of opportunistic pathogens, we know that it's been increasing over the last 20 years. We've seen a more than 500% increase in cases. In 2018, there were over 10,000 cases reported, and that's widely acknowledged to be an underestimate just because we don't test every community-acquired pneumonia case for Legionnaires' disease. Statistically, about half of these are due to potable water that we can trace back to a potable water source. On average, they're 9% fatal, but that of course goes up depending on the population that's exposed. And really outbreaks occur due to one specific species of Legionella called Legionella pneumophila, and even more specifically than that, a very specific serogroup 1, that causes the most of, or that's linked to disease most frequently. And typically outbreaks occur where there are multiple preventable failures from a plumbing design or operation standpoint. So that's very important to recognize as well. So why is this incidence of opportunistic pathogens increasing? It's first of all because of improved detection and diagnostics. So CDC made Legionella a nationally reportable bacteria, meaning that when a case is documented, it has to be reported to the health system. So that helped with tracking it. There were also really simple diagnostic tests developed called urine antigen tests that pretty much every medical lab can perform on a simple urine sample to diagnose for disease caused by Legionella pneumophila, serogroup 1. So we've gotten better at detecting it and diagnosing it, but as a population, we're spending more time indoors, so we're exposed to the built environment and the aerosols that we generate inside that environment to a higher degree. Our demographics and immunocompromised status of our population is changing with rising levels of obesity, elderly, people with asthma, allergies, or other chronic underlying diseases. And then one that we'll talk a little bit more in depth about is the development of sustainable buildings in cities. So while it's a much needed goal to conserve water and energy resources, some of those water conservation features can change water quality to make it more likely to grow these opportunistic pathogens. And we'll talk specifically about that a little bit later. So it's kind of my opinion that opportunistic pathogens are and will continue to be a primary public health battlefield in our century that we're currently in. The next paradigm shift that I want to talk about is the source, or where these organisms live. So traditional pathogens are fecal-related pathogens, and we have very effective methods for disinfecting or removing these pathogens at drinking water treatment facilities. So unless there's a kind of unanticipated event like a water main break or something of that disruptive nature, there's really no source for these traditional pathogens in modern drinking water systems. But opportunistic pathogens are basically can be identified or detected in all aquatic environments. Legionella has even been detected in rainwater puddles on the side of roads in Japan. So they're literally everywhere that water is, including our potable distribution water system. The next paradigm shift is exposure, or how infections are caused by these organisms. So traditional pathogens, we actually have to ingest the water to be exposed to them because they're gut-related pathogens. But for these opportunistic pathogens, the primary route for Legionella and a few of the other opportunistic pathogens is actually inhalation of aerosols. And there are other ones that we are exposed to through contact, either through an open wound, like Pseudomonas causing skin infection, or in our eyes. So there's an amoeba called a canthamoeba that can cause eye infections when it gets into the eye. And it's interesting that there are particular ecological relationships that these opportunistic pathogens can take advantage of that make them more able or more easily able to survive in drinking water. And the primary example of this is Legionella's relationship with its host organism, amoeba. So amoeba, through a process called phagocytosis, it basically wants to feed off of bacteria in the biofilm on pipes. And Legionella, being a biofilm dwelling organism, is part of that. So the amoeba takes up the Legionella as if it's going to use the Legionella as a food source, but Legionella can actually resist that mechanism and can take over the amoeba host organism cell function and use the nutrients within the amoeba, the amino acids, to grow to very high concentrations. And so they kind of turn that mechanism around on the amoeba and use the amoeba as food. The amoeba also exist normally in what's called a trophozoite form, where they're kind of grazing on bacteria. But when they're exposed to stress, and that could be high temperatures or a disinfectant residual chemical, for instance, they can encyst and become a cyst. And within that cyst, that it becomes like a very hard shell, essentially, it can protect the Legionella from exposure to disinfectants. So that way, when the disinfectant naturally dissipates with the chlorine reacting with the biofilm, or the high temperature decaying as the water sits stagnant, when that stressful situation goes away, the Legionella are re-released into the environment, and this process kind of starts over. And it's actually through this process that Legionella can become trained, or they kind of gain the mechanisms to infect human macrophages. So through this process, they actually become more infectious to humans. So that's an important factor here. And then the last paradigm shift is the regulatory framework, because of course we have regulations for the traditional pathogens with the total coliform rule. We have treatment processes and monitoring requirements for these pathogens in our drinking water systems, but for opportunistic pathogens, there's no such requirement. So you're kind of left to deal with this on a case-by-case, building-by-building basis, which is the crux of many problems with dealing with these pathogens. And there's a lot of information out there regarding how to control Legionella in different water systems or building types. Unfortunately, a lot of this information is not fully prescriptive, so it doesn't really tell you exactly how to go about having the best control over Legionella. And in some cases, the recommendations actually contradict one another, where one recommends one temperature and the other one recommends a different one, or how you respond to positives for Legionella. Those can be very different depending on the resource and source that you're getting your information from. ASHRAE 188, of course, is the first standard that applies to control of Legionella in building water systems, and it presents minimum risk management requirements. And at the core of 188 is this defining the water management team, which really gives this group of individuals the final decision power on the controls that that building actually takes. And this water management team really depends on the type of building that that you're talking about, but it can include people like facility operators, maintenance personnel. If you're in healthcare, it would include infectious disease or infection control people. It could include physicians and administrative people as well. But notably, not many of these people are experts in Legionella. They're not likely experts in drinking water quality, but they do have this kind of institutional knowledge about how the system operates, and so they're a critical component of that team, but they may not have all the skills and knowledge to round out what you would need for effective control. So I want to give you kind of a high-level example of what happened in Quincy, Illinois, surrounding a disease outbreak in 2015. And this occurred at the Veterans Home in Quincy, Illinois. It's a very large campus. It's got 48 buildings with about 30% occupancy, meaning that there's a lot more building than what is currently actually being used. So the water as well is very much being underutilized. And of course, being retired veterans, the residents have many risk factors for exposure to opportunistic pathogens. In 2015, the initial outbreak consisted of 220 individuals reporting that they were sick. 57 of them ultimately tested positive for Legionnaires disease through the urine antigen test, which included 12% of residents being diagnosed with Legionnaires disease, which is a very high attack rate for this disease. And the majority of this initial onset of illness occurred between August 21st and September 10th of 2015. And so if you look at the primary epidemiological curve for the disease, or when the cases occurred, the majority of the cases were linked to an issue with a water heater in water heater maintenance. There was a faulty valve. One of the two centralized boiler systems was taken offline and set stagnant for about a month. And then just after August 1st, that heater was put back online without any sort of treatment. So basically a month-old stagnant water got redistributed to the entire building plumbing network. And very shortly after, they saw a spike in Legionnaires disease cases. And they have had continued issues with control over Legionnaires disease because they've had continued cases of Legionnaires disease in 2016, 2017, and 2018, despite taking numerous steps in 2015 to remediate the system. And they still had Legionnaires disease cases because they still had Legionella pneumophila in their system. So if we look at their historical monitoring data that they had on site of the Legionella pneumophila serogroup 1 culture positivity, so the number of positive samples as a percent basis over time, they initially had some success in the disinfection, but by the middle of 2016, over 20% of their samples were coming back positive for Legionella pneumophila, suggesting that they didn't have very good control over Legionella growth at the time. Then in September of 2016, the positivity dropped dramatically, Yet they still had cases of Legionnaire's disease indicated by the red data points there on the graph. And we think that kind of looking at this retrospectively, that they had cases while they had very low positivity, because in late 2016, this first vertical black bar here, they had actually started monitoring for routine water chemistry parameters like chlorine. And so we think that they were actually increased their flushing time in order to achieve a residual before they collected their environmental sample. And when you flush the water before you collect your sample, you artificially lower your likelihood of detecting Legionella if it's there, because you're replacing that stagnant water with fresh water from the main plumbing system. And then in 2018, things were pretty contentious around this time. If you recall, if you're familiar at all with the Illinois politics, there was a governor's race in 2018, and Governor Ronner was up for re-election, and now sitting Governor Pritzker was basically trying to crucify Ronner's administration for their response to this Legionnaire's disease outbreak. And things got pretty heated on the House of Representatives floor debate, where one representative actually said to another that they would like to make them a broth of Legionella and pump it into their water system of his loved ones, so that they can all ultimately die. So it's pretty kind of extreme politics here. They had a lot of visits to the Quincy system over this, and a debate that was all focused about the response in Quincy. And luckily, more cooler heads prevailed. And in the middle of 2018, they actually reached out to our team to see if we could help determine why they had continued positivity at the facility in 2018. And so we switched them, sorry about that. We switched their primary disinfectant residual from free chlorine to chloramine, which was the secondary disinfectant residual that was provided by the municipality that Quincy system was provided with. And in doing so, they dramatically decreased the positivity of culture results, and luckily haven't had any more Legionnaire's disease cases since that time. But so in our investigation, it's really important to consider kind of all avenues of exposure. And while the main issue that was identified on the Quincy retirement home campus was this water heater maintenance issue, there is this question about what was happening with the municipal water treatment, wherein we see there are 5 total cases that were not related to the facility at all. So there were 5 cases that occurred in the community around this same time that would have had no exposure to this water heater maintenance issue. And so we wanted to look at that as well. And so we ended up looking at the distribution system disinfectant residual that was in the main water distribution system. And what we discovered was that there was a period of time where the municipality had stopped dosing the corrosion control treatment that was a phosphate-based chemical. And during that time, the disinfectant residual was pretty low in the distribution system, particularly located very near the veterans campus that we've been discussing. And so they were making these treatment upgrades at the water treatment plant, and when they had gone through this 6-month period of making treatment upgrades, they reinstated the phosphate dose, and shortly after, the disinfectant residual improved over time, kind of begging the question what was going on with the distribution system with the control, because in the middle of this time, without any phosphate corrosion inhibitor is when the initial Legionnaire's disease outbreak occurred. So our current hypothesis is that there was this seemingly small change at the utility level that precipitated this at-risk facility to kind of initiate issues with their Legionella control. And it's also important to note that this lack in phosphate has secondary impacts as well. So if we look at community-wide pneumonia cases in Adams County, where Quincy is located, in 2015 there was a spike in the Legionnaire's disease cases, or a spike in community-acquired pneumonia rather, which could potentially be undiagnosed Legionnaire's disease in the community, across the entire community system. And Flint, which we'll talk about here in a little bit, is another example where this might have happened as well, where they estimated that there were potentially 70 additional deaths due to exposure or due to the changes that happened in Flint, Michigan, which we'll talk about here in a second. The other impact here was that there were issues with the lead and copper rule compliance. So when they stopped dosing their disinfectant residual in their reporting period in December or in January of 2015 to December of 2017, their lead levels spiked during that reporting period that corresponded with the lapse in phosphate control. And unfortunately, there was a large spike in children with blood lead levels above 10 micrograms per deciliter just 1 month after the lapse in phosphate. So while this is not directly related to control of Legionnaire's disease, it's here to highlight the fact that these things on a system level are inherently interrelated and connected and have to be viewed holistically. So, I hope what this case study highlights is that there's no one size solution, there's no silver bullets for what treatment can be applied to any one system that would work for every other system, but instead it really requires an integrated understanding of opportunistic pathogens, plumbing system design, operation, and the engineering controls that we have in our available toolkit in order to control opportunistic pathogens. Okay, so I want to take a little bit of a side step for a second and discuss biofilm, because this is a topic that is, I see often referred to in a way that suggests that maybe people don't have a full understanding of what a biofilm is and what its function is inside pipes. So the first thing that we have to realize is that if we have a surface of any kind, including the interior pipe surfaces in our plumbing, we're going to have a biofilm. So biofilms are going to exist inside metallic pipes, on and within the corrosion scale that occurs in iron water mains. They're going to occur on PVC and PEX pipes, as well as copper pipes. And so the biofilm will always be there, but depending on what material is there, the types of microorganisms and the numbers of microorganisms might change significantly. Biofilms are really viewed as a kind of a living thing, but in reality, they consist of inorganic and organic materials. And the materials that they consist of can make it very difficult for disinfectants to fully penetrate that biofilm. So if you think about like a very thick biofilm with microorganisms growing throughout the biofilm, and chlorine residual being applied in the flowing water in the pipe, that chlorine might react quickly enough with the biofilm on the first layers and not actually penetrate all the way down into the system or into the biofilm because it's reacting with that inorganic and organic material. So that's important to note. The other thing that's important to note is that biofilms consist of a lot of bacteria. There can be over 1 million cells per square centimeter. They can consist of over 1,000 different species of bacteria. And so it's important to recognize that no drinking water is sterile. It's really the communities of bacteria that can allow these pathogens to grow to high numbers that are concerning. It's not the fact that there's bacteria there at all. And we talked about the primary example of having that amoeba host organism there with the Legionella kind of infecting the amoeba, taking over its cells and growing to high concentrations and being re-released into the environment. And so they're very complex and diverse. And there's a whole ecology of what's going on within these biofilms. So up in the left top corner, we see necrotrophic growth. So as the microorganisms in the biofilm die, other microorganisms are going to come and feed on that dead bacteria because it's a carbon source, it's an energy source for them. There's all sorts of selective things going on with whether you're applying a high temperature, that's going to select for thermal resistant microorganisms. Or if you apply a certain type of disinfectant, it's going to select for certain types of microorganisms. So every choice that we make in the design and operation of our system can impact the types and level of organisms that are there. And there's just no way getting around them. And they're really diverse. So if we look at just materials that are inside a shower hose, these are just a cross section of shower hoses. Depending on the water quality and the nutrients that are there and the pipe materials, whatever these individual materials are made out of, it can result in vastly different biofilms. So that's the take-home message here, and we'll come back to this in a little bit more detail later on. Okay, so now let's take a kind of a more holistic view of this control of drinking water systems, and let's go from treatment to tap, and we'll start with the municipal system factors that can impact opportunistic pathogen growth. And so that has to deal with the water treatment plant as well as the water distribution system. And the first thing that I want to talk about is corrosion control. So we touched on this with the case study in Quincy, Illinois, with the lapse in corrosion control potentially impacting opportunistic pathogen growth. Another example of this was in Flint, Michigan, when Flint switched their water source from purchasing water from Detroit Water and Sewer Authority to drawing up and treating the Flint River water. And when they did that, they didn't implement any type of corrosion control. And so they had rampant corrosion throughout their distribution system. And I'm sure you've seen the news media articles about this. And lead got a lot of attention, lead leaching and the discoloration of water, but the Legionnaires disease incidence got a little bit less attention relative to the lead. And so during the 2 summers that they were using the Flint River water, there were 2 very large outbreaks of Legionnaires disease consisting of over 90 cases and 12 deaths related to the switch. And just to kind of show or demonstrate how the infrastructure is not fully there at a systematic level to respond to this, it wasn't until January of 2016, so the winter after they had switched back to Detroit Water, that the public was even notified about this incidence of Legionnaires disease. So that's important to note that we don't have all that infrastructure there to the degree we need to ensure that reporting is getting translated to the public. And so during this time, we noted that there was more Legionella pneumophila in the water in large building systems, particularly hospitals in Flint, on the Flint River water relative to on the Detroit water. So we were sampling in October of 2015, just before the switch back to Detroit water, and we found that 52% of samples were positive for Legionella pneumophila. Relative to March of 2016, just a few months after the switch, where 2% of samples were positive for Legionella. So there was something about the Flint River water that was more conducive to colonization. And so we believe this was related to the more corrosive water. So, you know, the more corrosive the water, the more iron is going to corrode. That iron is released into the water and can become a nutrient source for Legionella. Iron is a nutrient that we add in extreme excess when we're trying to grow Legionella in the lab, trying to culture it under controlled conditions. So iron could act as a nutrient. But potentially more importantly, that iron, as it corrodes, it consumes the free chlorine disinfectant residual. So if you look at the free chlorine residual during the 2 summers that Flint was using the Flint River water, there were portions of the Flint water distribution system at the municipal level that very rarely had a chlorine residual. And so if you don't maintain a residual in your distribution system, you're less likely to be able to control that, the growth of Legionella once it enters the building plumbing system. And then in addition, there were an excess number of water main breaks, about 5 times more water main breaks during this period than normal. And when you have that kind of hydraulic disruption, it can release a lot of sediment and biofilm into the water, which can contribute Legionella on its own, but that also contributes surfaces for growth to occur on, and that sediment can also work to consume the disinfectant residual, making it harder to prevent the regrowth of these bacteria in the system. And it was in the highest water age or highest water residence time portion of the system that had the majority of the Legionnaire's disease outbreaks. And you can literally see the difference in the Flint River water from the time that they were not using corrosion control to the period that they had switched back to the Detroit water. And this is a picture taken about 6 months apart from the exact same tap under the exact same conditions. So, you know, Flint highlights this importance in a very extreme way, admittedly, that water chemistry is a potential governing factor for opportunistic pathogen growth. But it highlights the fact that, you know, while it's an extreme scenario that happened in Flint, more municipalities are going to be seeking alternative water supplies to meet future demand, and how that change in water source will impact the opportunistic risk is a question that we have as we move forward with addressing that issue. Okay, so that's corrosion control. The other impact here that's really, really important is what secondary disinfectant residual is used in the system that is being that we're talking about. So municipalities or utilities have 2 options for maintaining a secondary disinfectant residual in their system, either with free chlorine, which is generally viewed as a more powerful oxidant, meaning that it reacts faster, but is generally less stable over time. And they have the option of chloramine, or commonly termed as combined chlorine, which is generally more stable, which might help offset how quickly free chlorine tends to react and decay. There have been a couple of studies that have suggested that systems that are provided with a monochloramine or chloraminated water are much less likely to have Legionnaire's disease outbreaks than systems that are on free chlorine. So one study, in a case control study of hospitals, suggested that hospitals with free chlorine were about 10 times more likely to have a Legionnaire's disease outbreak than a system that was supplied with monochloramine. So it's more effective for Legionella control. But there are certain trade-offs here that we have to be cognizant of. And one of those trade-offs is the fact that when you introduce chloramines, while you decrease the prevalence of Legionella in the water system, you might increase the prevalence of other opportunistic pathogens. And the one that's been identified and studied the most is the increase in mycobacteria, which again is another lung-related disease-causing bacteria that occurs at similar frequency to Legionella, but it's not nationally reportable. So we have a little bit less data about its occurrence and control. But a couple of systems have studied this, and when they switch from free chlorine to chloramines, the prevalence of mycobacteria increases in their system. This has been confirmed in other field studies as well, and in 2 laboratory-controlled experiments. So we have good evidence that this really exists. So, you know, how to really navigate that choice with choosing one disinfectant to take care of Legionella, but making other opportunistic pathogens more likely is something that we haven't really fully been able to navigate yet. We don't have the research or work to demonstrate what we should do yet. So that's secondary disinfectant residual, and then there is distribution system maintenance. So we have more than 1.5 million miles of water mains in our country. We have more than 210,000 water main breaks per year, and that has increased by 27% over the last 6 years, and that statistic is about a year and a half old now. So, you know, as our infrastructure ages, the American Society of Civil Engineers has given us a rating of, or a grade of D or D- for our water infrastructure. So as that infrastructure ages, we're going to have to find ways to better maintain it through appropriate material selection, and infrastructure upgrades, and specifically flushing water to offset this issue of water age. Okay, so let's transfer now from this kind of holistic picture of water distribution system into some of the scenarios that can occur in domestic plumbing that impact water quality. We actually have quite a few engineering control strategies that are at varying levels of development and that have varying levels of success for controlling opportunistic pathogens. So I'm not going to go through all of these. And we've already talked about secondary residual type and water main upgrades. So I just want to go into a little bit more detail at the building level. Specifically, there are building plumbing system supplementary disinfection options that exist, and they range from, you know, providing supplemental chlorine or chloramine, depending on what your distribution system uses, to dosing alternative disinfectants like chlorine dioxide, copper silver ionization, UV light, and ozone, which is not really an option for building plumbing systems. And it's important to note that each one of these has, you know, benefits or a main draw for why you would implement it, and some limitations in terms of what you might want to consider if you're going that route. So I'm not going to go into detail here, but the slides will be available to you, so you can go back and read these. And so there are a bunch of different strategies. And the EPA has a very thorough document on the success and failures, or limitations rather, of each of these systems that you can read in more detail at the link below. So I do want to talk about controlling water age and water heater set point, because these are very important factors for controlling opportunistic pathogen growth. Again, at the municipal level, we have reduced the amount of water use that utilities are having to meet. So in a survey of 130 utilities, 60% of them sold less water in 2012 than they did in 2006. And 7% of these sold 25% less water, meaning that their demand went down by 25% over a period of 6 years. And this was viewed or termed the original conservation conundrum, because for the vast majority of utilities, for 70% of them, 96% of their revenue is directly linked to how much water they sell. So if the utility is selling less water, they have less water for operations and maintenance, capital upgrades, and staff to perform all those tasks. So that revenue is really important. The other conservation conundrum that we've become more aware of in the last 10 years or so is this factor of water age. So total water age can be viewed as the amount of time that is spent in the water system. So that includes the distribution system water age from the water treatment plant to a building property line or point of entry, and then the premise plumbing water age, which is from that building entry point to individual points of use. And both of these water ages can vary widely depending on where your building is at in your distribution system, or how frequently your outlets are used in your premise plumbing system. From a sustainability or green water system standpoint, some of these green water systems have new water quality characteristics. So there's some people that are wanting to use rainwater for their building water systems. There are all kinds of technologies to conserve energy surrounding water treatment or water heating and distribution in buildings that might have an impact on water quality. And in general, our fixtures over time have gotten much more efficient, meaning that we're using less water per toilet flush or urinal flush or per minute at the sink. And all of these things can impact the water residence time or water age within a building plumbing system. And so conservation conundrum 2.0 is the fact that this water age is directly associated with water quality issues that are chemically related, biologically related, and physically related. And many of these water quality issues are directly related to a potential impact on public health, meaning that they can increase people's risk due to water age. And so this is true at the distribution system level, and it is inherently true and more variable in building plumbing systems due to the variability of building usages and design and operation parameters. And so importantly, what we don't know right now is how COVID is going to impact all this. So I'm calling it the COVID conundrum for now. And we don't know if this is going to be 3, 4, or 5.0 because we really don't know the extent to which it's going to impact health exposure. But the stay-at-home orders are definitely leading to lower water demand in buildings currently. And all the same issues of water age apply, but now they're going to be more widespread to a higher variety of building types. And we're going to be talking about a different level of stagnation than we've encountered before. So whether it's a holiday break or weekend stagnation in a typical office, now we're talking about stagnation of potentially months, which might change the nature of some of these issues in a degree that we haven't anticipated. So if you're interested about learning more about this, I'm going to share a link with Lance to a free webinar that I'm going to be talking about specifically about COVID and restarting buildings here in the coming weeks. So I'll share that with Lance, and he can send it out. But in buildings, in typical buildings, we have this concept that as soon as we turn on the water is of good quality, and that's just not the case for many, many buildings. So in one case study that I was a part of, we went in and we flushed the water in the morning. This was a Friday morning, so it's not as if there were been a weekend stagnation. Just flush the water to see how long it would take to get water that was representative of the distribution system. And so that's what you see here. Total chlorine is a function of flushing time, and it took 80 minutes of flushing at 1.4 gallons a minute to see a disinfectant residual at this tap. So it's realistic that at a tap like this that might be used for 20 to 30 seconds at a time, a couple times a day, it may never actually see a disinfectant residual, which, you know, that's one thing. But then the next question is, even if you do achieve a residual at this outlet, how long does it last? Once you shut off that water, if you come back in an hour or a half a day or a day, is that disinfectant residual still there, preventing the regrowth of harmful bacteria? And what we saw at many taps that we monitored is that within just a couple of hours, the residual that we had achieved at that point of use tap had almost completely dissipated. So that means that if you have to flush for 80 minutes to achieve a residual and then it goes away within an hour or two, it's likely that there's never an adequate amount of disinfectant residual in many building plumbing system distal outlets. So, you know, that brings up the question about how frequently do we have to flush in order to maintain adequate residuals to prevent growth of these pathogens? And that's a question that we really just don't have the answer to right now. It's research that we need to do. However, I've done a little bit of work on this, and I've seen that for more infrequently used taps, so taps that are more characteristically, you know, not used, the residual tends to decay faster. So with increasing water age at a tap, the residual decays more quickly, which is good news because that suggests that if we exercise our taps regularly enough, we may be able to improve the stability of chlorine and maintain it. But of course, it's going to dissipate over time as it sits stagnant. So the next topic that I want to talk about is this debate on the effects of flow. So if you talk to any Legionella expert, they're likely to tell you that you know, flow is better for Legionella growth, with the idea that the stagnation leads to more opportunistic pathogens. So for many years, the mantra among plumbing experts was, you know, eliminate dead ends and you're good. And of course, that's developed over time as well. But there are a couple of observations that are counterintuitive to this kind of conventional wisdom that suggest that flow can actually support the growth of more Legionella. So in one experiment, continuous turbulent flow had 10 to 30 times more Legionella in the biofilm than completely stagnant conditions. And the researchers hypothesized that this was because the continuous flow, under the right circumstances, was delivering nutrients rather than delivering a disinfectant. So that's the hypothesis to kind of explain this discrepancy. Flow is better for Legionella control when flow is delivering high temperature or chemical disinfectant to taps. But flow is more beneficial to Legionella growth when it actually delivers ideal growth temperatures and nutrients to support their growth. So I wanted to study this in an experiment in a well-controlled experimental apparatus here on Virginia Tech's campus. And so I designed two identical hot water systems. One I made at 40 degrees Celsius is kind of like a worst case growth scenario at very ideal growth temperatures. And then the other I varied from 40 degrees Celsius up to 60 degrees Celsius to see what the effect of temperature setting was. And instead of just studying temperature alone, because we have a pretty good idea that high temperature kills Legionella, I wanted to study the impact on distal tap use frequency and how that impacts or mediates the temperature control. And so I studied these distal taps that had high, medium, and low simulated use, either flushing once a day, 3 times a week, or once a week for high, medium, or low use. And I removed all disinfectant residual from the influent water to again test the worst case scenario. And what we saw in the continuous flow portion of the recirculating system, so in the tank in this main recirculating line in our system, we saw that in the 40 degrees Celsius system with continuous flow, the levels of Legionella actually increased to very high levels because we're at ideal growth temperatures, we're recirculating the water, we're basically just delivering nutrients to the biofilm for Legionella growth. But in the experimental system, as the temperature increased, we were no longer able to support Legionella pneumophila growth in that biofilm associated with the high temperatures, just like we would think with our conventional wisdom. But of course, once our hot water goes into our distal outlets, that temperature decays as a function of time. And the vast majority of time that water sits at a distal outlet, it sits at ambient room temperatures, essentially, more than 99% of the time for most outlets. So even if you have 60 degrees Celsius in your water heater, that's going to cool off to growth temperatures eventually. I wanted to study the impact of this water heater setting, temperature setting, on these distal outlet growths. And to do that, I looked at what I called a regrowth factor, where I'm comparing how much Legionella is coming out of the distal tap relative to what was in the recirculating line. So I'm only looking at how much Legionella grew in the distal tap. And so a value of 1 here, because this is on a log scale, indicates that there's 10 times more, or an order of magnitude more, Legionella pneumophila in the distal taps relative to the recirculating line, and a value of 0 here indicates that there's no change from the recirculating line. So in the control system at 40 degrees Celsius, we saw pretty much what we thought we would see. At high use, because those taps are being turned over frequently enough, there's not really enough time for additional regrowth to occur. But in low use taps at 40 degrees Celsius, it sits around for a week and it can regrow a little over half the log more. At the highest temperature setting, we also saw about what we would expect to see, with all of these essentially being no change from the recirculating line levels, because the water's so hot that it's basically just disinfecting everything. But at 51 degrees Celsius, which is, if you continuously maintain that temperature, it's hot enough to inhibit Legionella growth. But if it's only periodically exposed, it may not be adequate. And so what we saw in that scenario is in the low use distal taps, we saw almost 70 times more Legionella pneumophila in those distal taps relative to the recirculating line. And what we think was happening here was we were seeing thermal selection for Legionella, because that 51 degrees Celsius water would come into the pipe and it would disinfect all the stuff that was easy to disinfect, but Legionella may be hanging out inside their amoeba friends. In assist, were protected from that thermal disinfection. So as soon as it dissipated over time, then the Legionella could be released from the amoeba, and then they're growing on all the dead microorganisms that were thermally eradicated by the 51 degrees Celsius. So this is kind of thermal selection for Legionella. So this demonstrates that the impact of temperature is dependent on the temperature setting, but also how often that distal tap is exposed. And there's potential, even under recommended settings of 51 degrees Celsius, for unintentional selection of Legionella at some distal taps. So that's really, really important to kind of acknowledge that limitation in some low use taps, that in systems that are kind of barely meeting that thermal disinfection guidance. So the other aspect about premise plumbing that we should talk about is flow rates as well. So flow rate may impact the opportunistic pathogen growth too. There's been now about 20 years of experience where metered, hands-free, or electronic faucets are more likely to be colonized by Legionella and other opportunistic pathogens than their manually operated counterparts. Unfortunately, we don't have any peer-reviewed literature on this to date. Even though we've known about it for about 20 years, there's not been really good controlled assessments of why this is. A lot of hypotheses about how the water volume is mixed between hot and cold, the different materials in the faucets, and many faucet manufacturers have made a lot of changes based on some of those findings. but we don't really have a systematic way to explanation for why this might be. And one hypothesized impact is the impact of low flow rate is, first of all, decreasing the volume delivered to the pipe. So you're increasing the water age, maybe facilitating the time required for these opportunistic pathogens to establish and grow. But with the lower flow rate, there's also lower pipe velocity. And so that shear velocity that we would maybe rely on to regularly remove biofilm and sediment that accumulates in our piping systems, that sediment might accumulate. And that can provide nutrients for growth, it can provide surface area for growth, and it provides a material for the disinfectant residual, represented by Cl2 here, to rapidly react with and dissipate the chlorine residual faster than it otherwise would, making these pipes more likely to grow opportunistic pathogens. So low flow may support the growth of these opportunistic pathogens as well. And then the last topic that I'm going to talk about is pipe material selection. And I want to start with copper because it's a really interesting one to me, because pretty much every impact of copper has been documented in peer-reviewed literature. From the notion that it has no impact on colonization or numbers of Legionella, it has been documented to prevent colonization or even disinfect Legionella. It's been documented to prevent colonization for a certain amount of time, but then over time becomes less effective. And then there have been a couple of observations where it actually has been documented to support or facilitate the growth of, or the colonization of Legionella, which is kind of counterintuitive by many trains of thought. So I embarked on a couple of years worth of investigation onto why or how we might explain these variable impacts. And from one concept, the observation of having no impact might just mean that it's the wrong form of copper. So copper speciation and copper solubility is very highly affected by pH, and the most biocidal form of copper, cupric ion, Cu2+, the actual ion, is much less likely to be present in water in typical drinking waters than just regular soluble iron or soluble copper ion. So if we look at, for instance, at pH 7, while there's about 60% or so of the total copper that's present is soluble, less than 25% is present as this most toxic form. And the biocidal capacity of the copper is drastically impacted by pH as well. So there's just one experiment on this that suggests that at pH 9, where you would anticipate much of the copper to be precipitated out, is not effective as a Legionella control, whereas at lower pHs, pH 7, it is very effective. So if you have no impact from copper, it's likely that it's just not bioavailable or it's in the wrong form. There's this concept of the temporary benefit of copper, and that can be attributed to the aging of copper pipes over time. So there was one study that looked at Legionella colonization in different materials over time, and initially copper material was less likely to be colonized and have lower concentrations of Legionella in the biofilm. But after a couple of years, all the materials kind of started to overlap and look similar. And this is likely because copper, when it's brand new, releases more copper ions to the water. It can act as a biocide initially, but then as you routinely use water in the pipe and you establish a insoluble scale layer, that copper releases fewer copper ions to the water, and starts to behave more like an inert pipe material, like the stainless steel or PEX. So this temporary benefit is explained by copper aging. And then I did want to mention PEX pipes, obviously the Plastic Pipe Institute, and there have been several reports of PEX pipes leaching contaminants or contaminant migration from PEX materials. All sorts of different types of compounds. And the one, or I guess the group of them that is kind of most concerning from an opportunistic pathogen standpoint is the leaching of organic carbon that could be used as a food source for bacteria to grow on. But there's been some work that suggests that while in kind of simulated and controlled conditions, PEX does initially leach a lot of carbon to the water, that the amount of carbon that it leaches pretty quickly dissipates over time. And this was a dump fill type of experiment protocol where we would expect that normal flowing pipes might be, dissipate the carbon leaching even a little bit faster. And there's some follow-up investigation that would be needed in terms of how bioavailable this organic carbon that's leached is. And so I've done some preliminary experiments that suggest that, even if the pipes leach a lot of carbon from the pipe material, only a small fraction of that carbon is actually able to be used by bacteria for their growth. So my personal kind of analysis of the literature does suggest that pipe material is important. Depending on the pipe material that you have, you're going to have different types and levels of microorganisms there. But specifically for opportunistic pathogen growth, my reading of the literature suggests that there are other overriding factors that are more important to influence the growth of opportunistic pathogens. Specifically that being temperature control and presence of disinfectants, whether you're using a chemical oxidant or heavy metal like copper and silver ions to control Legionella. So yes, while material is very important, I would probably base your material selection on other factors other than opportunistic pathogen growth than temperature, ability, or exposure to oxygen or sunlight. Those things are more important than the control of opportunistic pathogens in well-maintained systems. Okay, so with that, the takeaways here are that we have a need for routine monitoring and communication guidance. We can't operate these systems in a vacuum. And right now, I believe that the burden is disproportionately placed on building owners and operators, and we need to establish a better infrastructure for them to get help from the people who can help them make these kind of water management decisions. We've discussed some of these trade-offs, and basically for every decision that you're going to make in a building water plumbing system, there's a net positive and a net negative to that decision. And so it's really about being aware of those trade-offs. Really important ones being the selection of free chlorine versus monochloramine, what that means for opportunistic pathogen control, as well as the other water chemistry that would be involved. Monochloramine, for instance, is a little bit more complex to dose and control than free chlorine. There's limitations to every strategy, and of particular importance for opportunistic pathogen control is that most strategies for controlling opportunistic pathogens are dependent upon the water flowing regularly enough to deliver that control mechanism, whether it's thermal or chemical control, to the distal point of use, because all of the mechanisms that we have to control opportunistic pathogens decay as the water sits stagnant at individual points of use. And so the overall take-home message here is that teamwork is really needed with on-site knowledge of the system and how it operates and what's going to work best for their maintenance crew and how their facility and institution works. You need that deep understanding of water quality so that you can help predict and anticipate unintended consequences. Of course, there's the infection control and prevention aspect if you're in a medical facility. And then ultimately monitoring is the only way to really truly assess the potential for risk in your system. So with that, I would like to say thank you. Again, I work at Virginia Tech, and I did my PhD with Marc Edwards and Amy Pruden. Joe Falkenham and Annie Pierce were on my dissertation committee. They're very, very knowledgeable about mycobacteria for Joe and green construction and sustainability for Annie. And of course, I've got to acknowledge my financial support and other people that have helped me along the way. So with that, I would like to say thank you, and then I guess Lance, I will let you take over and sort of field some questions, and we can chat for a bit. It looks like we've got about 45 minutes or so, I believe.
Yeah, wonderful. Thank you, William. A lot of information, I'll admit, to everybody. It's a lot to digest, a lot to take in, especially since, as you explained, William, in a lot of these cases, the evidence doesn't necessarily lead you down a single path towards a single solution for a lot of different plumbing systems. So each system kind of has to be evaluated on its own, it seems in some cases. But I know we've got a lot of people that have been holding on for some questions. I have been following some chats along the way, so I'll call on some of those people to see if they want to speak out loud with the questions, and then we'll just open it up to everybody else to see what other questions people have been holding on to. Christian Harold of Teal Plastics, you had some chat questions early on relating to the effects of Legionella on the population. Did the presentation answer your questions, or do you have some follow-up questions to those? Are you still with us?
I am. I think the presentation largely answered the questions. That it came up a few slides later that the increase in the incidence of opportunistic pathogens is probably at least partially explained by the aging population. I think you went right into it about 2 slides or 3 slides after I asked the question. While I have the mic, I did have one other question that I jotted down. So it came up a few times in the presentation indirectly, and that is the effects of the pH of the water and control of water pH related to the effectiveness of your disinfectant chemicals and your disinfectant residuals. Is that something that you studied? Did you do careful monitoring of pH of water as you were going through the process to see what effect that had on Legionella and other opportunistic pathogens?
Yeah, so that's something that, pH is one of those master variables, and like anytime I set foot in a building or working on a project, it's something that we monitor and or control depending on if it's an experiment. I think the major takeaway to think about pH is if you're using copper and silver, it's critically important to control pH because of the precipitation issue. If you're using free chlorine becomes much less effective as an oxidant at higher pHs. So you want to make sure that if you're on a system that has a higher pH and you're wanting to use free chlorine, that you have a way to monitor and maybe even control pH. And if that's the case, then you might want to look into other disinfectants that are not as pH dependent, because I can tell you right now, for the run-of-the-mill building owner and operator to monitor pH is one thing, and control it is very, very difficult. There are systems that do it that are commercially available that are very good, but it's just another variable that can make your treatment much less effective if it goes awry. So that's really important for copper and chlorine in particular. pH is less important for chloramines, although it can kind of alter the amount of different forms of chloramine that form. So chloramines primarily in drinking water environments exist as monochloramine, which is the preferred form of chloramine to have, but pH can alter that. So you want to, I think pH above 7.5 or 8 is going to be totally adequate. You got to kind of get into crazy stuff for pH to really impact chloramine, and then pH doesn't impact chlorine dioxide. So that's another attractive option for a lot of people. And then of course temperature is not pH dependent.
Very good. Christian, did you have any other follow-up questions to that?
No, not right now. Let me think about that for a minute.
Okay. We'll open the floor up. I've got a few questions that I've been saving, but we'll open the floor up first to members who may have any questions. If you find yourself muted, you may have to wiggle your mouse around the screen to find your image to unmute yourself. If you click on the little GoToMeeting picture that shows the two heads with the number 65 beside it, you may have to scroll down to your name on the list and possibly right-click and unmute yourself that way.
So as we're waiting for people to chime in, I'm going through the chat here, and I saw one about chlorine dioxide. So I just touched on that a little bit. That is a common chemical to use for Legionella remediation. It's got some limitations that you would want to be aware of. For instance, it doesn't last very long, so you can't really expect it to stick around in your system. But as a remedial treatment, it is very, very effective for Legionella. But then you also want to be asking questions about how that chlorine dioxide interacts with your pipe materials. So it can cause the water to become much more corrosive. So that's a problem for some metallic pipes. And then something that Lance is leading through PPI is an investigation of how it impacts plastic pipes as well. So there's some preliminary evidence that it might cause plastic pipes to become more brittle, but it's unclear about the time duration of exposure. And if you're talking about something like a remedial action, it's less likely to have kind of a negative impact than if you're in a long-term application of chlorine dioxide.
Yeah, good point. The PPI research project that is looking at chlorine dioxide right now, it's a multi-part project that really just initiated 2 months ago back in March. Kate Ollinger from Uponor is chairing that project. The project number is BC-2020-01, and the task group is quite large. There's Kate. Hi, Kate. The task group has over 20 people, 25 people involved already right now in various subtask groups. But if anybody on the phone today, yeah, I can hear someone. But if anybody on the phone today would like to get involved with that task group, please contact myself or Kate, and we can add you to the task group.
I remember a call.
That's somebody else. I've just remind everybody to mute yourself if you don't want us to hear you. William, a couple of follow-up questions. One thing you just talked about with regards to remedial treatment of the water. So I assume that means if there's some sort of an outbreak and all of a sudden you need to knock the level of Legionella down, you do a high temperature dosage or disinfectant dosage or something extreme for a short duration. What is typical duration for those different types of remedial actions? Is it a day, a week?
Yeah, so it really depends on the system. So let's see if I can think through it on the fly in a logical fashion. If you're talking about temperature, so first of all, you got to differentiate between hot and cold water systems. Cold water is much less likely to have issues with Legionella because it typically maintains a residual better. The residual decays faster at higher temperatures, so cold water is, the residual is more stable. Cold water is also frequently, not always, but frequently, it's in the lower range of the Legionella growth. So Legionella is much less likely to grow in it because the temperature is just not right for it to grow. But having said that, there are some instances where you can run into that type of issue in cold water. But the majority of issues occur in hot water, and they're usually poorly managed hot water systems. And what I mean by that is either hot water temperature that is not adequate at the water heater, or a large hot water distribution system that is not maintained properly. And what I mean by that is specifically balanced. So you want to make sure that if you have a large, complicated hot water system, that hot water system, that hot water is being delivered to the whole system. If you've got one zone that's getting hot water and one zone that's not, that zone that's not is at higher risk. So for large systems, it's unlikely that temperature alone can be an adequate remedial action, because we typically don't size water heaters to provide hot water enough for all the buildings to adequately do a hot water disinfection appropriately. Smaller systems have a better chance at that, and that would be maintaining 70 degrees Celsius for 30 minutes. So that's just really hard to do in a big building. If you have a building that is currently unoccupied and you want to perform a remedial disinfection, you can do that quickly within a couple of hours with high levels of chlorine dioxide, or chloramine, if that's what you want to do. But if the building is currently occupied, then you cannot really pump in high levels of disinfectant without restricting access to the water and a whole bunch of extra stuff. So what typically happens in those scenarios is, they inform people about the risk of Legionella. If the health department determines that there needs to be a physical barrier, they have to install point of use filters on every outlet in the system. And then a disinfectant residual can be added to the water and dispersed throughout the water system over the course of a couple of days to a week, making sure that you're maintaining adequate levels of residual for several days. And then you kind of go back to normal operation. But when you go back to normal, you want to make sure that you've kind of gone through the list and said, why did we have this problem in the first place, and start to identify the design or operation issues like dead ends or an imbalanced hot water system that have led to the issue to begin with. So it can really range from, a day-long activity to, a week or more. And then once you've done your disinfection, you want to take samples to confirm that you have disinfected the water immediately. But then you want to go back, a couple weeks later to make sure that those other systematic issues that may have been present to cause the issue in the first place have been addressed, and that you continue to have good control over the Legionella.
Quite a challenge. So many variables.
Yes.
Thank you for that.
And so when you do these disinfections, you get a professional involved, someone who has experience doing the water treating, and they come with protocols and infrastructure to help the building through all the decisions that need to be made.
Okay, thank you. We have a question via chat from Jonathan Simon of Lubrizol. And Jonathan, I'll read your question, and then if you want to add to it, feel free to speak up. His question, as written, says, this issue is commonly looked at in the realm of larger commercial building systems. how does the dynamic change when considering smaller water distribution systems in residential buildings? Jonathan, is your question simply, do we need to look at residential plumbing design to see how to prevent Legionella there? Or could you?
Yeah, certainly, thank you, Lance. The broader question for me is we haven't talked about this in the context of, say, single-family homes or smaller individually plumbed multifamily townhouse type systems where you potentially water age becomes less of an issue, but there may be some other concerns that haven't been addressed because it's always been looked at in the context of larger commercial buildings. So I was curious to see the perspective on, does the way that we look at this change if we're talking about smaller residential buildings versus larger commercial structures?
Yeah, so this is a really interesting area because and there's a couple of different thoughts that go into it, and I guess I'll just hedge at the beginning of my answer to say that I don't really have the answer. But so a couple things to consider is, one, residential systems are much less likely to be colonized with the bacteria due to the better water age, but there are aspects like the unused tap in the basement, shower or utility room that can be problematic. The storage and distribution of hot water in single-family residential systems is typically much more straightforward. There are some design aspects that I'm not really sure exactly how they'll play out with respect to manifold systems versus on-demand versus recirculating. Like, I would definitely say that on-demand hot water systems are like the best way to go because very low retention time, you likely retain your residual, you're heating at the point of use, and that sort of thing. There are risk factors that make homes more likely to be colonized. So one of those that's widely known is being in older parts of distribution systems, so the age of the home and the age of the pipes in the distribution system, so that's a risk factor. Another one is having an electric tank water heater that's heated with electrical heating elements relative to a gas water heater. And the logic there is that many times when the electric water heater is not being used, the hot water rises to the top of the tank and the tank can become stratified. And you can have very amenable temperatures at the bottom of the water heater where sediments and nutrients can accumulate. The other aspect with the electric heaters is that the bottom, there's typically two elements in them, and the bottom element is exercised more regularly because there's a dip tube often that comes in and puts the cold water at the bottom of the tank. So if you use just a little bit of hot water in your water heater or at a time, the cold water is going to come in and cool just the very bottom of the tank, and then the bottom element will be turned on and off more regularly than the top. So what happens is the bottom element then craps out on you over time faster than the top element, and then you have a larger volume of water that's stored at ideal temperatures. So that's a factor, but it's very individualistic on a case-by-case basis. So after all that hedging and saying that it's less likely to be colonized and there are known risk factors and all that, the other aspect is that 96% of Legionnaires' disease is sporadic, meaning that we don't know the source where it came from. It's not identified with an outbreak, and it's not identified with any one source in particular. So one hypothesis is that the exposure of people to Legionella in homes is more significant than we really think. And there have been a couple of case control studies that sort of support that, but then others that say that exposure is low. So I think that's an area of, if we can get some more epidemiological infrastructure to study that would be really helpful. But in general, we typically think of single-family residential systems being lower likelihood for colonization. And then the final thing that I'll say on this is that it then depends on the susceptibility of the host. So even if you have Legionella colonization and you have a transmission route, you know, someone who's not immunocompromised or not susceptible to these is less likely to be infected by them than someone who's immunocompromised. So we might even be able to start thinking about you know, how we make recommendations to people when they go and see their physician. For instance, if we could do some education on the side of, oh, you're in this risk group, like what's going on at your house, and have a little informational brochure that can take care of some of that risk, because they can operate at a higher temperature or make sure they're flushing their water or what have you.
Yeah, I came across a report. I forget who the authors were. About it's only a few years old. It was about an older gentleman living in his private family home in Wisconsin, who ended up getting Legionella, and they did an analysis of the plumbing system, and they found fairly high levels of the Legionella bacteria throughout the different water distal points through the plumbing system in the home. So certainly it does happen. I think in a lot of cases it's just not detected because nobody gets sick, like you said. So.
And if you come in with a sporadic case, I mean, so you get community-acquired pneumonia, so then you have to rely on someone to test you for Legionnaire's disease. And once you're diagnosed, you know, there's a very good infrastructure to make sure that our epidemiologists at the state level are identifying outbreaks. But if they can't identify your case coinciding with another case, either spatially or temporally, then there's just really no infrastructure for the health department to get involved and help that homeowner or that, you know, that individual investigate where their disease might have come from. So it's just very challenging, and we don't have the infrastructure to say, oh, it's a sporadic case, here's a toolbox that people can go to help determine if they're exposed at home or not. It's really just assumed, okay, it's a sporadic one-off case, and from a public health perspective, we don't have the infrastructure or resources to investigate to the degree we would need to.
Sure. Okay. Ritual has a question.
Yeah. Hey, thanks, Dr. Rhoads. This has been great. Apologize, I did have to miss a little bit to jump on another meeting, but I came back in when you started talking about the reduction in flow rate and the impacts of velocity. Have you guys done any quantitative studies or determined how big of an impact, you know, the reduction in velocity caused by the reduction in flow rates has had on the growth of Legionella?
So we're starting that work now, and we've done one project so far that really suggests that it's most like the Legionella regrowth in the pipe is mostly related to water age rather than the actual pipe velocity. So if you control for everything else and you have a very high flow rate tap that has the same water age as a very low flow rate tap, then that individual tap is basically the growth of Legionella is dependent on the water age. But the context here, and the reason that I didn't really go into depth on this project, is that studies one outlet, one distal branch in isolation in a very controlled manner. And it really says nothing about the fact or the impact that would be present in a whole building system that has a bunch of these taps. So if you've got good water quality entering every single tap, our preliminary data that is not peer-reviewed or published, by the way, suggests that, you know, that you're probably okay. But when you have a bunch of these all next to each other or all in the same building, then that decreases the water quality within your whole building system. And we know that type of increase in water age is related to an increase in risk for Legionella. So it's my suspicion that it may be the combination of factors that is really critical to achieve to see that negative effect. But we're still like sort of working through that data and iterating on those findings.
Yeah, and just to follow up on that, we've had some discussions obviously with Dr. Edwards through PPFA about doing a water quality study based on pipe sizing and that kind of thing. And one of the reasons for this is if you look through the plumbing code, really sizing has not changed since the 1940s when Hunter's curve was developed and that kind of thing, when essentially you had communal bathrooms in hotels and so the number of fixtures that were in a building and the sizing, we're still sizing the same way, but we have so many more fixtures. And when you look at it, you're basically sizing, assuming that 75% of the showers in a hotel are all running at the same time, and we all know that's just simply not true. There's some anecdotal evidence out there that suggests that number is down closer to like 15%. So yeah, the water age in the trunk lines becomes a major contributing factor, a major potential issue, which is why we wanted to start taking a look at this in this project of right sizing plumbing. So I was just wondering if you guys had any evidence or any information at this point in time that would suggest that is truly a real issue.
Yeah, so I think that's the concept that we're kind of working towards, right? Like if we believe that it's not inherent to the velocity alone if you've got good water quality entering the pipe, but it's about making sure that you've got good water entering the pipe. That is definitely a sizing issue if you want to use low flow rate fixtures. So that's kind of one concept or hypothesis at this point. We don't have the data to really support that is the case. But on the sizing issue, I've been talking with folks at IAPMO about their model that they've been using for multifamily residential with Appendix N or M or whatever it is in the new code.
Appendix M.
And we're starting to discuss the data that is needed to expand that model to other verticals. So if anybody on the call has information about water demand patterns or the ability to get water demand patterns or collaborate with people who can install sensors and that kind of thing, that's a path that I'm starting to go down to try to expand that model to other applications, because I think it's critically important for sure. The sizing is very, very important.
Good. It's not good, but yes, I completely agree. And look forward to discussing that in much more detail down the road.
Yeah, we're restricted by the code. So I see a comment from Dan Holmes, the hands of our design engineers are tied, and like I talk to plumbing design engineers pretty frequently, and they lament this fact every time I talk to them. So it's that we need to make progress.
Good. Amit Lathia of CSA has a question, and I'll read it out, and then Amit, feel free to supplement. So the question is, does it increase probability of Legionella when a person basically leaves the house for the winter? So let's say a lot of snowbirds from up north go down to Florida for the winter. The house basically sits empty for 6 months with no flow. In a lot of cases, I think those people would actually even turn their water heater off, I think. And then the question is, then when they come back to the residence, what are they likely to be faced with then? So I guess it's almost a two-part. What if they leave the water heater on? What if they leave the water heater off? Are they better to turn the water heater off? I'm kind of supplementing Amit's question a little bit here, but
yeah, thanks.
I've never.
I think you put it very well.
Yeah, so I'm not aware of any direct guidance on what exactly to do. I think it's widely acknowledged that the snowbird effect does increase risk when you return home to a stagnant plumbing. There are recommendations for how to flush home plumbing systems, including the water heater, and if you have filters, and like it's a pretty thorough flushing. Lance, I will send you a link to that and allow you to distribute that to people. But yes, when you return home, I mean, even from a week or so vacation, I would be thinking or considering about, doing some sort of flushing of my system to, just to turn over the water in the system. So yeah, and whether it increases probability, I don't know for sure, but I would suspect that it would because of the stagnation and weird things can accumulate while the pipes sit stagnant. I would, if you're going to be gone for a whole season, I would personally recommend that you turn off your water heater because when it's on, leaks are more likely to happen. You're consuming energy that you don't need to consume to keep it hot. You're really only treating the one volume of hot water, and the rest of the system is sitting stagnant at ambient room temperature, so there's no real benefit there. But when you return, you should definitely crank up that heat before you start using the water, because if you've accumulated a lot of stuff in your water heater while you've been gone, you want to make sure to crank up the heat and thermally disinfect that heater before you start flushing your fixtures. So there's some guidance that I'll link to Lance and he can distribute.
Okay, great, thank you. And as a follow-up to the conversation you and Ritual were having a minute ago about pipe sizing and volume and velocity and things like that, I've heard you speak on that topic before about the surface area to volume ratio of a pipe. Is there any kind of an ideal ratio of what is the ideal? Well, yeah, is there a perfect surface area to volume ratio that would help guide pipe designers if their hands weren't tied in a code-defined world?
I don't think so. I don't think so at this point. So the concept, for just so people are kind of following along, when you decrease the diameter of the pipe, which would be one solution to decreasing the volume in the pipe and increasing the pipe velocity so that we can use smaller flow rates. So when you decrease that diameter of the pipe, the amount of surface area per unit volume of water increases. So we call that the surface area to volume ratio. So per volume of water, there's now more surface area for attached growth. There's more surface area for the disinfectant residual to react with, and it might decay faster, particularly in metallic pipes and particularly in new metallic pipes that have not developed that insoluble scale layer like copper aging does. So what that trade-off is, we know that it likely exists, but its dependency on material and disinfectant residual and background water quality has not yet been thoroughly explored. So I think that's an area for future research that I'm interested in to help inform that. But the idea is that as you get smaller, that ratio goes up, so those reactions kind of increase. But there's no ideal and there's no limit or threshold that you should be worried or concerned with. It's just the idea that if you're trying to solve one problem, meaning solve the velocity problem or water age problem in pipes, you might be creating another problem that we should understand more before we run off and do that immediately.
Yeah, so ultimately there might be
in this industry.
Right, and for so many of these things, what we're looking for is that sweet spot where we can optimize all our settings to minimize the growth of the OPPs.
And then the simple reality is that you could probably make anything work with the right operational parameters. But, like in response to COVID even, we're having all these conversations of, oh, you should flush your pipes, and even answering the most basic question, well, how frequently should I do that? We don't have good science-based answers for that question yet. So there's a lot of unknowns here.
Definitely, wow. Dan Holmes, you had submitted a few chats. Did you have any other verbal questions for William? Okay.
Yes, I'm sending one right now.
Oh. Okay, here's Dan Holmes' question. Are the biofilms found in Los Angeles the same that would be found in Nova Scotia, Miami, and Alaska? That's our four corners there of the continent, I guess.
Yeah, so I mean, the very, very simple answer is no, most likely not. There'll be certain groups of microbes, bacteria that will be similar at certain levels. But when you get down to, species level identification, Legionella or Legionella pneumophila, the ratios, types, and amounts of those specific bacteria are going to be highly variable. And they're going to be highly variable within a given water distribution system, depending on building size, operation, design, materials used, all these factors. So the short answer is it's just going to be really, really highly variable. There are people that are working on this concept of, what's a core safe microbiome, or what are the types or levels of microbes that typically don't lead to the growth of pathogens. But that's still kind of an exploratory, new and exciting area for research. So not something that we're ready to plant a flag down in yet.
So if I could follow up verbally.
Yeah.
Can you hear? Okay.
Yes.
So with that said, as we move forward with water management plans, and I know the industry has a tendency to do copy paste. Not a good thing. Every building needs to have its own specific risk assessment done and its own water safety plan developed from that. But realistically, if you found something that would work in Miami for control of bacteria growth and so forth, if you were in New York City, that same type of method might not work there, even if you had similar things in a building, correct?
Yes. Yeah. So that's
I'm talking at a very technical level here. But water doesn't care. Water is going to do what it wants to do, where it is, when it wants to, and it's not so much, we're not in control of that.
Yeah, so I mean, that's certainly true for a lot of things. There are, these core components that are beneficial no matter where you are, such as maintaining your hot water heater, like your hot water generation above 140, maintaining your hot water return at all points at a minimum of 120, 130 if you can do it. So there are those types of overarching recommendations that are effective everywhere, but how you implement them in a certain building is really going to be impacted by the features and factors in that building.
Exactly. Sure. So as a follow-up, you had mentioned hot water temperatures. Now we have a lot of information in the industry running our water at 140. There's code issues or changes that are looking at right now to go to 160 F. Obviously, we have our domestic hot water side where we especially on the hydronics, that's non-potable, of course. We run 180. If you're in a kitchen in a domestic potable system, you increase the water temperature to 180 through the disinfectant of the kitchen utilities and so forth. But we have not done long-term testing of piping systems, domestic piping systems at 160 and 170 degree temperatures. And although we're trying to kill off, say, the Legionella microbes, which is, certainly something we want to do, we haven't looked at the unintended consequences that could be coming from that, the failure of the piping materials, the gasketing materials, and so forth. So I just want people to be careful of some of this type of stuff as they, maybe think that this is all I got to do to kill, kill some bacteria. So anyways, I'll mute myself and
Yeah, so I mean the temperature is interesting because, you know, okay, by 1 degree hotter is better because the hotter you go, the faster it kills. But you know, there's a point of limited return, you know, per degree Fahrenheit or Celsius increase. And so all the recommendations that are coming out or that have come out from, you know, committees of people, ASHRAE, you know, 2000 update, the the National Academies of Science and Engineering report on Legionella are all suggesting 140, above 140 is good. So to go up the 20 degrees higher is in my view, a pretty extreme and not recommended step. It has the potential for unintended stuff, as you mentioned, for sure. So yeah, I think that, and I'm aware of those code changes, and I think that we should be careful on how we do it. And I mean, some commercial water heaters aren't even designed or rated to go that hot. So they really only do it, you know, for temporary disinfection, and you know, so I agree completely.
Yeah, and as a advocate for plastic pipe, yeah, we would caution against that as well, not just for the potential
Sure.
lifetime of the plastic pipe itself, but there's also data out there that those high temperatures combined with certain disinfectants also damage metal piping systems. And everything that's downstream of even the main distribution pipe, fixtures, faucets. How does that react to elevated temperatures, whether it's a gasket in the faucet or some of the other plastic materials and faucets and fixtures? We don't know. So yeah, I don't think we're trying to move the needle towards hotter temperatures beyond 140.
Yeah.
Plus scald issues and everything else. So
the other aspect here is that, you know, it would likely push people towards, you know, like, so you can't fully distribute 160 degree water. You have to temper it somewhere. So one option would be to temper it at the, you know, point of generation with a master mixing valve. And if you do that, then you're going to increase the water age in your water heater tank because you're going to be using less volume of hot water because it's hotter. Then the other option would be to temper it at the point of use using, you know, thermostatic mixing valves beneath the sinks and things like that. And that's problematic because those things, you know, clog and fail all the time. They're kind of a maintenance nightmare. Who knows what's going to happen at hotter temperatures? And downstream of them, it's like less likely that they're going to have controls because you've eliminated the thermal control downstream of that mixing valve, and you're diluting it with cold water. But then that cold water is reacting with hot water, so the disinfectant residual is going to decrease rapidly as well. So, you know, for all these reasons, it's, you know, hotter is maybe not better in this case from above 140 as a you know, standalone recommendation. I won't disagree that there may be certain applications where it's appropriate, but not as a blanket statement.
Yeah, well, thank you. Well, we've come to the end of our time here. As for the official schedule, on behalf of all our members here at PPI today, William, we really want to thank you for your time and putting the presentation together and delivering all the content in a way that was digestible for us. You covered a tremendous amount of information. Thanks so much for all the Q&A. That was really helpful. And one thing I think we should do, because we've been collecting publications on Legionella for years, and just basically they're sitting on the shelf, so to speak, electronically. I think within PPI, I think we can set up a folder within Spec Builder. A lot of our voting members have access to this online platform called Spec Builder, and we can actually set up a database there where we can start to post some of our publications there so our members can get access to them. So for the members who are still on the call, stay tuned for hopefully an invitation in the next few days to get access to a new PPI Spec Builder home, a database for Legionella publications. So.
Okay, yeah. And I promised to send you two things. I think one was an invite for people that are interested in COVID specific building stuff, and I can't remember what the other one was.
There was a study about flushing of water. This was following the snowbird question about how often should I flush my residential plumbing system.
Yeah. Okay, yeah.
I think that's what it was.
Recommendations for flushing home plumbing. Got it.
Yeah, that sounds good. So, okay. Thank you so much. Any last words for us? And we do recognize that you are part of the BCD project that I mentioned earlier, the BC 2020-01 on chlorine dioxide, and you've been helping us through that project already with your guidance and information through that one as well. So much appreciated.
Yep. Yeah. No. So yeah, thank you so much for having me. If there's any, you've got my email. If there's any follow-up, would love to hear from you.
Okay. And we will be doing, within the next few days, posting a link to the recording of today's webinar within PPI member login, and we'll let our members know when that link has been posted. All right. Thank you again, Dr. Rhoads, and thank you everybody for joining us today. Bye-bye.
Okay. Have a good one. Bye-bye.